was a delay because I lost my clipboard. Anyway, welcome to the second day of presentations. Today we have attacking the data sparseness problem by the semantic analysis for sparse data group, and Luis Gattari will introduce the proceedings.
Hello, this is the third and final project of the workshop, and I'm myself and Roberto Basili were the co-leaders of the project. We had a very big team who all worked very, very hard. I guess I should say the presentations that follow really don't reflect who did the work. It was a huge team effort where I think you'll see the results. So the presenter isn't necessarily the person that did it. It's just that somebody who worked on it, and we really did consider it all a team effort. I'll just say a little bit about the motivation for the project. I worked a long time ago on text extraction, but in every natural language processing task, we're always in the business of trying to find repetitive patterns in text, and we'd like to do it automatically. And it's always a problem because language is so diverse and words are different. So even though these both describe in some sense that some organizations attacked some location somewhere, we could never get that from any sort of language modeling that used words because we don't have information. So we worked a lot on named entity recognition in this field and doing that, but we haven't done anything with common noun kind of things, and that's the focus of the project. What would be really nice to see eventually, that you could replace somehow these kinds of sentences so that you could see that they're both organizations attacking some location on some date. And that's kind of our goal. Could we ever do this automatically to text? And it would improve a lot of things. We could take trigram models over this, and we could extract patterns automatically. So we wanted to explore if we could do part of this problem. It was a 6-week project. And so we had to focus a little bit on what we could do in 6 weeks. Our hypothesis then is that if we could transform a corpus and replace words and phrases with some sort of very coarse semantic categories that will help overcome the data sparseness problem that we see in language modeling and also in text extraction. We even have some evidence to show it might be helpful in machine translation. And we decided for the 6-week thing that we should tackle a sort of noun-centric approach. Could we do this for noun phrases? And if we could, maybe then we can gather some other information about verbs and adverbs and prepositions. So our 6-week goal then was to label noun phrases in a big corpus. So if I take that sentence, astronauts aboard the space shuttle Endeavour were forced to dodge a derelict Air Force satellite on Friday. What we would want to do is the first noun phrase is astronauts, we'd want to mark it humans. We would like to take the next noun phrase, the space shuttle, and replace it with some category that corresponds to the head of the noun phrase. And when we take the next noun phrase, a derelict Air Force satellite, we'd like to replace it again by a category that corresponded to the head of the noun phrase, and now we have some tom reference. Now, if we could do this for a whole corpus, we'd have a lot of gain. We can then look for all the things that are objects of the verb dodge, and all the things that are subjects of the verb dodge, and have some sort of repetition in the data. So there's a lot to be gained if we can do the task. The question was defining it in some reasonable way. So before the workshop, we had a lot to do. We had to somehow identify a tag set. We wanted to create a human annotated corpus, so we knew if the task was reasonable, if the tags we picked were reasonable, and so forth. And we wanted to have some sort of reliability that humans could do the task reasonably well and have some double annotation. Named entity recognition is something that we've done well, and Sheffield has a really nice environment, this generalized architecture for text engineering, where we put a lot of tools for named entity recognition. So we actually wanted to start out with at least a portion of the BNC marked with named entities, so we did do that. Fabio Zanzotto and Roberto Basili wrote a parser. I don't know how it competes with Professor Charniak's, but we parsed about 26 million words, so we had information about verbs, subjects, objects, and prepositions. We developed some algorithms. We thought WordNet is sort of the natural source for doing this job. But on the other hand, WordNet has lots and lots and lots of synsets, and deciding which one to assign is a hard task. And we looked at base concept, and we looked at unique beginners, and things that are in publications about WordNet, but they're all big sets. There are 1,000 things, and we didn't think we could really get very good reliability. So we went for the classes that were used to mark an electronic dictionary in England. It's Longman's Dictionary of Contemporary English. It's meant to be a learner dictionary. They define nouns in their dictionary with a set of 34 categories. Now, some of them are silly, and it allowed the lexicographer to collapse senses. But we wanted to somehow prune that set and come up with something that might be decent. The rationale was the number of semantic classes was small. They'd also been used by a whole team of lexicographers to code a whole dictionary, which is 56,000 senses. They assigned categories to nouns. They tried to define adjectives in terms of the kind of noun they like to be with, and verbs in terms of the kind of subject and object and indirect object they like. So at least there was some experimental evidence that maybe these classes weren't too bad. And in addition, many of the words in the electronic dictionary have subject area information. So you might say that bridge on a guitar is a movable solid for music. So there were kind of pairs of semantic category and subject marking that we thought we might make use of in the project. And we did have the annotators choose among those.
So just point
Yeah.
of information.
Uh-huh.
Is your goal here to try and do the semantic labeling to sort of learn to do semantic labeling on a large corpus, or is your goal to develop techniques that will allow you to port this semantic labeling tool to completely new domains?
Well, we hope the second will come out of it, but
it sounds like the first
for 6 weeks, it's what we aim for, and I think we have some things to contribute to the bigger problem. But of course, that's all of our goal. Everybody wants to mark proteins and protein pathways and genes, and there are a lot of common noun things for which there are applications, and of course we know that. But it was, what could we do from a sort of language modeling perspective? I'll just give you a little picture about the semantic classes. We tried very hard to make disjoint classes. I mean, wouldn't it be nice to say to the annotators, okay, is it solid, liquid, gas? Is it plant, animal, human? Is it abstract? We could give them real disjoint things, no problem with decisions. But it turned out we couldn't make very good use of the dictionary markings then, because the markings are hierarchical. And there are words like tapestry, where they didn't know whether it's a movable tapestry or a not movable one. Is it a huge one on the wall that you couldn't move, or is it a little tiny tapestry? So they just marked it solid, but not movable solid or non-movable solid. So in the end, we did remove some categories which were meant to capture two senses. Like, I'll give you an example. The word rhapsody or the word sonata are marked abstract or solid, because the lexicographer wanted to say you could either be talking about the sheet music, I suppose, or the abstract idea of a rhapsody or sonata. Well, fair enough, but we didn't want to give the lexicographers that choice. So we actually, when we presented things to the annotators, we separated that and said, choose between abstract or solid. So we took all the disjunctive categories that the lexicographers use and broke them up. So this is a basic set. As you see, it's mostly a division of the concrete world, and you could say, well, why didn't you work more on abstract? Well, we had a pre-team meeting where we tried to mark some text with finer qualities of abstract. Is it a state? Is it an emotion? Is it a quality? And it was very hard to get agreement among 12 people. Those things are actually, it depends on how you're looking at the sentence. And we decided that for a first cut, this was, we wanted to do a very coarse kind of marking that we should then go back and look carefully at. It's not as pretty as you think. There are some senses that are marked male and female in the dictionary, and they might be male animals and they might be female animals, or they might be humans. So the word she, for example, is marked female, but it's used in our text actually to mean, female baboons and also people.
Sheep, no? Sheep, no?
Chimps. Yeah.
Sheeps.
Oh, could be ships as well. But the instances I've seen in the data had to do with animals.
Was that
So-
animate or inanimate?
Well, it's meant to be animate. I put them there. So I'm trying to say there's some other labelings that are on different dimensions, and we had to deal with those. There are also some strange ones, physical qualities and organic things. What does that mean? Physical qualities are things like armful. It's not quite a human thing. It's kind of, we put it there as abstract, but they didn't really. And organic things, eczema is organic. Lots of diseases are organic. So there are a lot of strange words that we decided we're not trying to make any claim to this semantic category set. I mean, it's a philosophical problem and would go on forever. We're trying to start with something that exists and say, can we do this task automatically, assuming it's reasonably decent, and allow it to be refined. There's also one more dimension, and that's that we have things marked collective. So they could be collective things like a flock of sheep or a pride of lions, or they could be they can be group things for people, groups and organizations. Okay, so that's what we went with. These are our categories. I'll tell you some statistics. So we annotated 214,000 instances of noun phrases. We actually annotated a little bit more, but we allowed the annotators to skip doing the job sometimes. If, it could happen that there's a sense, a use that's not one of the semantic categories we provided them, and we felt we had to allow them to skip it. So, and we noticed in the data that, I don't know how reliable those are. I don't know how many of them just wanted to go home and they skipped the last few before they got out of the interface. So we removed those for all purposes of the experiment. We have 214,000 reliable marked with category noun phrases then in our experiment. It covers almost 30,000 vocabulary items. There are 25 semantic categories in total, and let's see, I guess we have to comment that almost a little bit more than half are marked abstract. A lot of language is abstract. Yes.
What was the human labor involved? How many annotators and how many person months? And how much overlap between per given noun phrase? How many annotators per noun phrase?
We did 10,000 instances by 2 teams. They weren't necessarily the same 2 people, but we doubly annotated 10,000 instances.
And the rest of them were just...
And the rest of them were single annotation.
Okay, and how much time?
And we did it in about 1 month. We have this very nice architecture in Sheffield. You'll see a little bit of it. And we had an interface made up from
and how
that.
many people per month?
We used 3 PhD students.
What else we wouldn't do with PhDs?
We try to get philosophy students. We have this theory that philosophy students make very good markers, but our own students volunteered. And is that right, Hamish? Did we take?
It was 5 of us, isn't it?
Did we have 5?
I think so.
Well, go on.
Hamish Cunningham, who is there, managed it, so you can ask him details. Okay, so our experimental setup then is this. We started with 26 million words. We chose them not to be from literature, just to keep the metaphor and autonomy down a little bit. We human annotated about 2 million words, noun phrases only. So now we have this annotated data, and we had to make...
One other question. So this isn't the same data the MT people have been using in English. I wasn't sure if everybody was using it.
No, we maybe should have used some of that data, but didn't. I don't know. There were lots of advantages to the BMC. We had run the named entity recognition on it before, and the formatting problems when you're dealing with a lot of data, they take a lot of time. They're boring, and nobody wants to hear about them. But it takes time to get everything to work with Gape, to work with the parser from Italy, to get to work with the new tools we want to develop to make use of the maximum entropy toolkits that we wanted to use is a lot of, you know, boring stuff that had to be done. So it was just a practical decision, I think. Okay, so I'll say a little bit about this. We used this development set, and it's not exactly random. We started with a randomly selected one. It had a very high baseline, and we wanted to look at some other interesting issues. So this is almost random with some extra hard words put in and held out. I'll just say that for now. We created also what we call a challenging development corpus by dividing this annotated set up a different way. So we have the blind portion set aside, and we said, okay, we would like to know how we do on unseen words, things we haven't seen in the training data. Now, it's hard to simulate that, right? Because we have to check how well we did on these words we haven't seen. So we had to create some experiment, and well, Fabio thought of this very nice idea, which is that we put all the unambiguous words in one part of the training and all the ambiguous ones in the other part. Now, that makes a tough task. So these are completely disjoint. There are no words in our training that appear in the held out. And on top of it, all the held out words are ambiguous. So, and some of them highly ambiguous. So it's a very tough task, but we wanted to see how we did on that. We think it's critical to see how we behave on unseen words. Okay, so in the experiments, in the talks you hear today, you'll hear results from both test sets. Some results are just on how do you do on unseen words purely, and how do you do on a more random, but still slightly hard training set. I'll describe it in more detail. So our experiments that you're going to see include sort of two tracks. We have supervised approaches, and by that I mean they use the training data somehow, a hard way or a regular way. We have unsupervised approaches that didn't use the training data at all. What happens if we didn't annotate, or you're in a new project where you don't have money to pay annotators and annotate? We use some outside evidence in a lot of the experiments, either the dictionary or WordNet. We use syntactic information from parsing or pattern matching, and we use the source context words. We use the use of preferences, both dictionary and corpus derived, you'll see, and we use some topical information. So you'll hear about all of this kind of thing throughout the morning. I'll just give you some real digest of the results. So on the very hard development set, this is exactly how it is. The training corpus has only words with unambiguous annotations. It came to 125,000 training instances and 73,000 in the held out. We said the perplexity is 21 because we could assign any, basically, of the classes. Three classes were, one class is unmarked, so that's essentially not putting a mark, so we didn't consider that. Our baseline on that was very low, 45% accuracy. That means mark it with the most frequent tag. If you've seen the word, that's what we use for the baseline. Here you haven't seen any. And otherwise mark it with the most frequent category that exists in the text, which is T, and it turned out in that data it was only 45%. We have added different methods to try to improve the accuracy, and we have had a nice, encouraging improvement through the use of some of the features, and you'll hear about that. Context can contribute greatly, we think, in these experiments.
What's accuracy means?
It means we had some special held out data that the annotators marked, but we removed the markings and developed a program on the training, and then had the automatic marking of this held out data, and then we had a little evaluation program to measure. Is that what you mean?
No, I mean, how do you define accuracy? What is this precision?
Well, this is exact match. Did you exactly get the category that the annotator got? What percentage of the time did you get? We'll talk about measures, but this one that I'm showing you is just absolutely exact match.
This is a forced match, right? This is a forced answer, so precision and recall are the same.
Are the same, yes.
Yes, sir.
It's precision and recall at the same time because we have one decision for each test instance.
So the reason I'm asking is if this is 45% of correct answers and the rest is undecided or is wrong answers.
No. There is always just one answer.
It means that they're 55% wrong. Exactly means that.
Means you picked one of the 25 categories that was not the.
Yeah.
Yeah.
Yes, we did something a little bit better than that for the baseline. We only allowed the categories in the baselines to be ones that were possible from the dictionary. So we knew what was possible. The annotators only annotated things from the dictionary. So our whole world, our whole event space, if you like, is things that appeared in the dictionary.
So, I mean, on a previous slide, you said something about 25 semantic categories. There weren't that many?
There weren't that many, but one of them is an unmarked category, one of them is a question mark category, and that's how we got
So your
25.
complexity was lower than 21.
Pardon me?
It was lower than 21.
Well-
How many categories were there?
Oh, I see.
Five,
Perplexity is.
weren't very good, we ended up using only 21.
There were 21 choices, but that
21
doesn't
choices,
even-
but you didn't always provide 21 choices for each.
And they weren't, and they didn't have all the same probability.
Yeah.
Okay, all right, so you,
So I should say choices.
Right.
okay.
Because
We usually-
perplexity
Perplexity
implies
is
some
something
probabilistic measure.
Well,
In this experiment, for example.
Could we take these questions later, please? I mean, accuracy is accuracy.
I think-
That's no great mystery here. So,
But
I put that here because the same measure is used on the next two slides that
Okay.
I'll give you, and
But I do have one question, which is, you said that abstract comprised more than 50%.
of the human annotated data.
Right.
But on this particular held out set,
Okay.
it must have been 45%, because that's what we would have guessed for everything. Okay, on the development set, perplexity measured through the same experiment we measured it before, and it's because they only looked at 21 categories in a few of the experiments. They chose to remove things that the lexicographers didn't mark, which we were counting in the 25. And there were 3 very small categories that were hardly used, and they didn't look at those, so they just removed them from the data. So that was why it was 21. These are figures from the same experiment. So using the same 21 classes, the perplexity is 3.44 on the baseline experiment, but we got 80%. And you'll see through the results today that we were able to improve the 87%. Yes.
So the dev set is completely, you just shuffled all the data all together. And
We did that first.
Have ambiguous and unambiguous categories.
And then we moved
That's
some-
the training.
And then we moved a few ambiguous words into helping. So we
And that's why
have,
it's also so much better.
oh, sure. I mean, here we had seen some of the training data. Okay, so we had this scheme. We wanted to develop things that worked well on our experimental framework with the training and the held out. But after doing that, we wanted to somehow use all of the annotated data, train on that to mark the blind corpus. And so we developed an incremental scheme within the maximum entropy framework, and I want to say a little bit about that. So several of the talks have to do with how we did the re-estimation and how we bootstrapped. So just give you a little overview. There's a distinction to be made then. We have seen words we've seen in the human annotated data. When we get to the new corpus or the blind data, we may see new instances that are in the same context or not in the same context. We have unseen words, meaning we haven't seen them before, but we do have information. They're in the dictionary. And we have novel words. So they're not in the dictionary or WordNet, and as I'm sure you all observed, you may have novel categories also, but we didn't consider that. We considered a more closed world kind of assumption.
Can you clarify? When you say seen, you mean that a test token, its type has been seen in training. When you say unseen, you mean that the test token's type is not seen in training, but it's in the dictionary.
That's right.
And then the third one is that
And
the
then
type has not been.
we don't know anything about it. Okay, so we start out when, at the end of all the experiments that you're going to hear about, we wanted to do something where we use all the human annotated data all together train a system on that and then mark the blind portion and see how we do. And that might give us some evidence as to how we would mark the rest of the BNC. So I should say that this data is 4 types. So the rest of the BNC, we ended up having 515,000 heads of noun phrases that were unambiguous. So we thought, might be good for training also. We know the marking on it. There were 550,000 that we had seen in the training data. There were only 9,000 we hadn't seen, and there were only 20,000 not. So that gives you a breakdown of the data we had yet.
When you say 515,000 unambiguous, what you mean is that in your current data, there was only one tag for them. So you're not ruling out.
No, we mean, take the head of the noun phrase, look it up in the dictionary. If it only had one possible semantic category, consider it unambiguous.
So it's
So
used as a different.
this may or may not have been seen. Well, it's a different dimension.
What I mean is that it could have been used in a different sense, which the dictionary.
It could, and we would
And you
miss
wouldn't
it
know.
because we absolutely used a closed world assumption. So we developed, the data we have is not very homogeneous. You might have that this noun is the object of a verb, but you might not have it for other nouns. Or you might have some prepositional information for some and not others. And even with the dictionary, some words didn't have semantic categories assigned. Some words didn't have subject areas assigned. So we had a problem that seemed well suited to the kind of exponential distribution that maximum entropy helps to estimate the parameters for. And so we wanted to do things within that framework. So most of the experiments that you'll see have to do with the maximum entropy experiment. But this is a kind of big picture that was saved for the end, because this is just really a technique for how do we do the blind data. So the idea is that we'd start both with the annotated data and this unambiguous data, that we would just make the assumption is right. We would try to learn enough from that to do the scene data. Now, in using this approach, it means that this data, we have to have sort of initial estimates for the probabilities in that data, and so we'll talk some through the talks about how we did that. And after things converge, after we estimate the parameters, the lambdas of the distribution, and converge, then we go back and re-estimate the probabilities for those, and do the maximum entropy again. When we feel we finally converge in the outer loops, then we move over to this. We performed this part of the experiment and this part, but haven't done anything with novel. We hope something can be done within this framework. Some interesting theoretical questions have come out of it, and well, I hope you'll keep that in mind in the talks that follow. I'll just say that on the blind data, just as a digest, even though we held aside 1/10 of the annotated corpus, we randomly selected it within each of the domains. It contained 13,000 instances. We ran a baseline, in other words, after training with very simple techniques, how well do we do? It was very high, higher than the development corpus we had. But we did manage to improve a little bit, so we feel the results are encouraging. You could say in some sense, well, that's not a great improvement, but we improved a third of what was left in some sense, and it's hard to make gains after that. So, well, I hope you look forward to the talks today that will describe the different experiments we did. So we started with a very basic bag of words experiment, not using maximum entropy, and you'll hear about that first, and Kalina will tell a little bit about some motivation from machine translation. So Kalina Boncheva, who's from Fashion.
Okay, so before I go on to the first experiments, I'll talk a little bit about some very small study we carried out for the purpose of machine translation and whether the knowing the semantic category of a word can help us with some choices. We picked 10 test words at random, divided the frequencies of the words in the corpus into three categories: high, medium, and low, and picked 10 test words from those. Then we collected their target translations using EuroWordNet, which gives you translations from English into 7 European languages. For instance, Dutch, which I'll be using on these slides. So one of the words that we picked, for example, is crane, and it has two synonym sets. One is corresponding to the sense of lifting and moving heavy objects, which translates in Dutch as those two words. I'm sorry, I don't know them, so I won't pronounce them. And then the other sense is for the bird sense of crane, and that translates as the other word. So what we did after that is I performed a manual mapping of the between synonym sets in WordNet and the semantic categories from logos that we used to identify that Louis showed earlier on. There is an automatic mapping based on probabilities, but Roberto Basili will talk about that later on. So what I did after that was I studied how many of the synonym sets were rolled out as translation on the basis of knowing what the semantic category is in addition to knowing the word. And some results for 3 of the words, there was full disambiguation. So if we know that we have crane, which is marked as an animal, then there will be only one corresponding synonym set, as we saw earlier on. The same is true for the medicine words, the abstract senses in the science of medicine versus the liquid or solid where you're taking the medicine drug. And for plants as well, the plant is plant versus the solid sense of the building where things are produced. For 7 of the words, the category, knowing the semantic category reduces substantially the possible translations. If we take the word club, for example, in the Dutch EuroWordNet, we have 5 possible synsets, which are the abstract sense, marked to, one of the first one is marked to the abstract category, in the sense of association of people, then movable solid in the sense of stout stick, or the other one is again movable solid, the club used by a golfer, or a playing card, and the final one is the building used by a club, so that's another movable solid. And in this case, if we know that in our text the club was marked as unmovable solid, then we have only one possible translation, and the same is true in the abstract sense of club. However, if we know that it's been marked as movable solid, unfortunately we still have 3 choices down here, which somehow got a bit messed up by the little filters. So these are the sort of very short experiments that we just wanted to show what the kind of indication we can get about whether this is useful for machine translation, but further studies are needed to do that automatically and actually measure it. The next thing I'll talk about very quickly is about the back-of-words approaches, and that was implemented as part of a sort of more general architecture, and it's based on the multiple knowledge sources word senses integration architecture developed by Mark Stevenson in Sheffield. And the idea is to allow the use of multiple taggers and combine their results through a weighted function, which you can learn from the corpus. And the advantage of that is that you can have the different taggers sort of vote on the data, and then you can pick. And hopefully, he showed that for word senses integration, being able to do that gives you better performance than any of the taggers on its own. So far, all the taggers that we've integrated within this paradigm are implemented as part of the gate system and are combined in one application, and I'll show you what that means. That's a screenshot of the gate system itself. As you can see, on the left-hand side, there is a baseline frequency tagger, which Louis mentioned earlier on, and all it does is for seen words, it just picks the most frequent category from the corpus, and for unseen words, it just picks the most frequent category in the corpus in general, which is the abstract sense. Then there's the bag of words tagger, which I'll talk about now. And there is one which just uses a dictionary and picks for every unambiguous word, it just assigns that category that is in the dictionary for that word. The bag of words tagger is a very simple one for the moment. It's based on an information retrieval sort of inspired tagger, where you collect for every instance of the training data with its semantic category, you collect a set of words that occur in a given context. So the parameters are the window size. By default it's 50, but it can be given as a parameter to the algorithm, so any value. We experimented with 10, 20, and 50, but 50 gave the best result. What part of speech to put in the content vector? By default it's nouns and verbs, but you can just specify what part of speech you want, and you can put also adjectives and adverbs, or just nouns. And then finally, what similarity measure to use. But I'll come to that later on. It's been used in word census configuration by by Leacock, and they got very good results from it. And so did we in this experiment. Here are some examples of what we derive from the data. So for the training sense, if we have created an animal as a marking, then we have words in the context like species, fertility, disease. For the multiple solid, we have worker, disaster, machinery. So we kind of interpret that really in the right sort of. So as I said, the scene words are classified by calculating the inner product between the context vector from the text with the vectors of each of the possible categories that is learned from the training data. And there are different metrics that we can use to calculate the inner product. The simplest one is binary vectors, discount the number of matching terms. Or we can have some weighted measures. I tried experiments with Leacock's measure, and they use it for word sense integration, and it favors concepts that occur frequently in exactly one category in the context vectors, assuming that that has more high disintegration power. And also, I experimented with measuring into account the listening of the concepts in the vectors. But I must say that the best result was just using the binary vectors and just counting the number of matching terms. The current performance measures, the baseline frequency tagger, so performed at 91% on the blind set. The bag of words tagger on its own, which means that it's not trying to resolve any of the unseen words, it's just resolving the seen words, achieves 92.7%. And then when you combine the two together, because the baseline assigns the most frequent category for unseen words, it assigns the most frequent category in the corpus, which is abstract. However, if abstract is not possible for that category as given by the lexicon, then it will assign the first category from the lexicon. So that's why this 91% is slightly higher than the standard baseline, which only assigns abstract to everything, regardless of whether or not you use the lexicon.
Just to clarify, the test set here, I remember there seem to be 3 test sets. There's the hard test set, the dev set, and the blind set. Is this what you're calling the blind set?
Yes, that's the blind set.
That was stuff that we never looked at until the very end of the project.
Okay.
Yeah. And so combined, these two taggers achieved 93.2% with window size of 50, using only nouns in the context vectors and using binary similarity. And the reason we used those parameters was because when we tested on the other sets, these were the ones that were giving us the best results.
The inter-annotator agreement was 94. Is
Yes.
that appropriate for the particular set that you're talking about? And should we consider 94 to be an upper limit to this particular test?
I think so. Yeah.
There's almost 95 actually.
Yeah, it's between 94 and 95, so you could say that 95 is the absolute upper limit.
Okay, and that's true even when you restrict to the smaller number of categories?
I think so, yeah. I mean,
I think I just deleted the slide. I can find you. I have the inter-annotator agreement on each category. Actually, I included. I'll tell you afterwards.
okay. So very briefly, some future work. We have some ideas how to integrate some syntactic information or also subject codes that Louise mentioned and document topics from the BNC into this sort of architecture to give us hopefully slightly better performance. We also wanted to experiment with the cosine similarity, and these are sort of the two easiest things to do in the future, in the immediate future. And then further along, we plan to experiment with the velocity-towards integration algorithm, how it will perform in this particular task, and also implement actually the learning of the weighting from the corpus, which hasn't been done now. And very finally, one of the interesting experiments will be to integrate also the maximum entropy results that will be talked about from the others as one of the taggers supplying preferences for the weighting module and see how all of that combine the performance together. And now I'll pass on to Chris, who will talk about how we evaluated our performance in a bit more detail.
I should say that Chris is the first of our undergraduates on the team. He's from the University of Sofia in Bulgaria.
So Elena gave you some numbers and Carol was right, and always was speaking about accuracy. So I'm here to describe how we measure our work and what we did to see whether one tagger is more or less correct. So if we're given vector of words, we're going to annotate, and we're given different annotation categories, and we get the result by a tagger with the corresponding vector. The most simple thing we can do is to assign 1 for each match we have and 0 for mismatch. So basically what we can do is simply define the accuracy to be the number of pairs where we have the same category. So that's what we usually do, and that's what we see most often, but nevertheless we have an hierarchy, and it's not smart to be completely ignorant about it. So for example, if you have a word to be a human and the tagger produces male human, is not that wrong. So what we want to do is to give a partial score for categories that have a answer relationship. So first we define a weight for each category to be the number of words that are in the subtree with root at that category. So for example, the weight of human will be the number of words that are human, female human, and male human. And then we score each pair to be the ratio between the weight of the categories, so that it's no more than 1. And we will define the accuracy to be this way to be the sum of the scores. Of course, if we have no answer relationship, we will give score 0 for those pairs. Well, that's nice, but if we get male and female, we will assign 0, which is not so good again. So we want to do something more, and that's to compute the similarity between the two category sets, and what we're going to do is to compute the distance between them. So we define the distance to be the length between the categories using simple path, and of course, so for example, for male and female, we'll get length 2 if we use if we assume that each edge has a length of 1. Of course, we can go with some information from the training data and define the length of each edge to be something more complicated, but we prefer the data and to use only 1. So what we get for the distance between x and y is the sum of the distances, and we know that accuracy 100% is 0 distance, and we get our distance, and we should know what is total disagreement. So we define max possible distance to be the sum of distances for each x in the maximal possible distance from this category to every other category. So this way we compute total disagreement, and we can find our accuracy. For some problems, it may be reasonable to use average function instead of max, because average will give us what is the expected distance if we pick a random category assuming equally probable categories. And to give some idea what we got with these measurements, if we get a training and have our data and the blind data, and we perform 3 baseline experiments using first testing word net because it's the most probable one, and random category for unknown words. First testing word net using T because T is abstract and it's the most probable category, and use the first sense in Morgan dictionary and T for unknown. What I mean by known here is words that have first sense to be a category that we don't use. So the exact match gives us these numbers, and the edge distance using average max gives these numbers here. And as we expected, the average distance is usually quite close to the exact match, depending. Sometimes it's a little bit more above or a little bit below, depending on the data. And the edge distance using the max function produces a little bit larger result because it's error tolerant. But what we can see from this slide also is that simply using dictionary we cannot achieve quite good results, and in fact using coordinate is harder task than using Wallman dictionary, and this is natural because we use Wallman dictionary classes for undating. Okay. So that was what I had to say about accuracy, and I'm going to pay attention to Paul's, who is going to present our first supervised maximum entropy experiments.
Can I just show me how to do it? Yeah, it's it's controlled. Yeah, I usually only use Linux and LaTeX, so it's, but anyway. So I'm reporting about supervised methods using maximum entropy, and this was a work which was done by Gia Huey, David Guthrie, Martin Pollock, Jeremy Wood, and me. Okay, so just an overview of my talk. I will first give a recapitulation about the maximum entropy approach. Then I will describe some of the feature functions we have implemented and tested during the 6 weeks. I will only present a small subset here, and these feature functions I will present in this talk will only cover context-independent features. So the other stuff with context-dependent features will be given in some later talks. I will then say a few words about word classes we have used in order to cope with the problem of data sparseness. And finally, I will conclude with some experimental results for the maximum entropy approach. So, okay, maximum entropy approach. In the maximum entropy approach, we have a framework in which it is very easy to integrate information from several knowledge sources and for classification. And these data for our classification problem is described usually as a number of feature functions, here denoted with this Fi. And these feature functions usually have to be defined by the experimenter beforehand. So this maximum entropy approach has some nice properties. One I have already mentioned before, so it's very easy to integrate information also from very heterogeneous knowledge sources in this framework. And another nice property is that this approach always converges to the global optimum on the training data. So if we have some features of our data, let's say, then we always reach the global optimum, or at least this algorithm will, this algorithm here, the generalized iterative scaling algorithm, will converge to this optimum. And if we apply the logarithm here before both equations here at the probability and the exponential function here, this will then vanish. The denominator here is a constant for the given observation x, and then we have only this term here with a constant factor before, and this is the reason why it's also called a log linear model. Okay, during the workshop we have used two maximum entropy toolkits. One is the Jasmer toolkit, which was written by Franz Off, and the other is the Jamie toolkit. It's just Gia's maximum entropy toolkit, and it was written by Gia, one of our team members. Okay, so all we have to do is now defining these feature functions here, and that is what I'm doing now. Okay, the first feature function we have defined is, of course, it's very straightforward to use a so-called prior feature. It's nothing else than using the unigram probability of all semantic categories. So this feature function is called f prior with the arguments w and c. W is our head noun, and c is the semantic category, one of the 21 semantic categories we have. In this case, we do not use the head noun itself, we just assign here the unigram probability of our semantic category. And then hope that this probability will also hold, let's say, from training to testing data. The second feature function we have defined is the so-called lexical feature. So we use the head noun itself as a feature. In this case, for example, if we have observed the noun lion, for example, then we use the noun lion as it is as a feature together with its class. So hypothesize that lion is an animal and it also occurs in the dictionary, then we use this information as a feature. So actually we could also use lion together with its hypothesized class as a feature, but here we have used only the dictionary in order to reduce the number of features. So this is not really necessary to look it up in the dictionary, but this can reduce our number of features, and we are still in the closed word assumption here. So if it exists in the dictionary, then this feature function will fire, and otherwise not. So the third feature we have defined is the so-called Longman preference features. So Longman dictionary provides, beside the words and the semantic category, which is here denoted as a tag, also the so-called subject code. For example, you see here that the word club occurs three times with the same tag but with different subject codes. And this means that club is, in this example, like in Kalina's example, this is a movable solid, but it has different meanings. In this case, it can either be a weapon, then we have the subject code military here, but it can also be a tool, for example, in golf games. Then we have here the subject code sports, or it can be a symbol on a card game. For example, Clock of Ace, I think it's called, or something like this. And then the subject code is here card games, for example. And what we have done here is that we simply count these things here, we look up them in the dictionary, and then assign the count to this feature function here. So actually this is an example for non-binary feature function, because this value can be in general larger than 0 or 1. So in this case it would be 3, and we would just assign the number 3 to this feature function f Longman preference feature. Some other features we have defined are these so-called unknown word features. As far as we are in this closed word assumption and we only find in the testing sets words which are in the dictionary, these things will not really contribute to our later results. But anyway, if we have complete unknown words, then these things could hopefully help. For example, the first feature here is the prefix feature. So we have as argument w our head noun itself that we have observed the hypothesized semantic category and this I, and we just assign the substring. This is some kind of C++ notation here, starting from the first character up to the ith character, I think -1, and this is then assigned to the prefix feature in this case. The suffix feature is defined similar, just we use the suffix of our string starting from the ith character up to the end. And this human IST feature is a special feature which is defined as a special suffix feature here. For example, if you have words like scientist or humorist and things like humans like that, I should say, then this feature will fire if the head noun itself ends with the suffix IST. This does not hold, of course, for all the usual names. For example, NIST, FIST, MIST also ends on this IST, but if we would use some further restrictions, maybe on the length of this word, then this could help. But anyway, it's a reasonable feature to define this here. Okay. just a few words about word classes. We will hear something more and more detailed about word classes in the later talks. The first thing we can do, of course, using word classes is lemmatization. So in this case, we eliminate all the inflections and reduce words to their base form. For example, the plural dogs, it would be reduced to the base form dog, and so on. Humans would be replaced to human, and so forth. This, of course, is an assumption that we made here because different cases of one word have the same semantic classes. This does not hold for all plural nouns and for all inflections, but this is an assumption we can make here. And we will later see that if we increase our amount of data, then this lemmatization will going a little bit worse. The other possibility to define word classes is mutual information. This is just a definition of mutual information. It just matters the amount of information one random variable has contains about the other random variable. So we can use this criterion in order to define some kinds of classes, and this was applied for nouns and adjectives, but these results are presented in some later talks. Okay, some results. These are results of the development data set. We have trained on 98,000 running events, and testing were on 101,000 events. So here you see our feature sets. This is the tagging accuracy. It's just 1 minus the error, or tagging error. And this is the test complexity we got on the test data or the development data in this case. So our first feature is the F prior feature. So if we know nothing except our unigram probability, then this will always assign the most probable class, which is in this case abstract. And we got a tagging accuracy of 58.8%, and the test complexity is then 5.52. So if we introduce this IST feature, I've already said this does not hold for all the words. We have only a very slight improvement. If it's really significant, I haven't computed this. So we came from 58.8 to 58.9. The test complexity also decreases by 0.01, so it's not very significant. And anyway, the suffix free feature means that we have used the last 3 characters of a word, and this increases the tagging accuracy by 61.6%, and also the test complexity is also low. If we use the prefix feature, this is most often a little bit better, because very often there's more information in the prefix of a word than in its suffix. So this is slightly better here, and if we also increase the prefix here, then we have 68.3%, and the test complexity is 3.41. And here we see this can go on. If we increase this number here, then we would have the lexical feature, for example. Then we have a tagging accuracy of 80.5, test complexity is 3.48, and so forth. And here we have the longman preferences as an additional feature, and we got an accuracy of 84.6%. And if we use the lemmatization here, then we can increase by around by exactly 1% here, so we yield a result here from 85.6%.
Now, these are individual. Are these cumulative or individual?
These are individuals. I also make some tests with, let's say, combine all these feature functions, but it did not really improve the things, because we are still running here in some kind of closed word assumption, and we find all words in the dictionary at least. So we cannot really expect that we find something from the prefix feature if we can do a lookup in the dictionary. So this does not really significantly improvements in this case. Okay, just one last slide on the experimental results on the blind data set. So you see here that the numbers are slightly higher in part than before. Oops, sorry. But what we see here is that now we have trained on around 200,000 events, and testing was on around 13,000 events. So in this case, everything is going up here, everything is going down more or less here. The only point is now that this lemmatization assumption does not really hold, because we have now enough data so that I think that this is a good indicator which shows that lemmatization as a word class here performs slightly worse than using directly the long math preferences without this kind of classification. Okay, that's it. And if there are no questions,
Okay, hi, my name is Jerry Liu. I'm in
One clarifying question. I think one of your remarks, I think I finally realized what it meant. You said you're not using any context features. By that you mean that you're only looking at properties of the
it
word.
means that I only use the head noun as it is without any looking at the neighboring or surrounding words.
Right, and that gives you 92.90.
Yeah, this yields these results here. And how to deal with context we will hear in the following talks.
Okay, so hi, my name is Jerry Liu. I'm an undergraduate at Columbia University, second of 3, and I'm going to be continuing on from where class left off, and I'm going to start talking about context features, and you can see the same bunch of slaves applied to this set of Maxent experiments. Okay, I'm just going to start with by giving a more detailed analysis of some of the results that class just presented. And then I'm going to rewind back to one of our feature functions, and I'll give a motivation for why we want to look at that again. And then I'm going to talk about some ways that we try to incorporate context features. And then something we like to call clustering methods, how to deal with some data sparsity with context. And then show some experiments results. Okay, so just when we thought we can go home with about an accuracy of 93%, it turns out that actually we're getting a lot of free points when we look up the dictionary, because a lot of things are actually unambiguous. So this doesn't really mean that we're doing anything very challenging. In fact, the Maxent model is probably a very big overkill to do that. So good to know that at least we're doing very well with ambiguous words that are seen, but the things that we've never seen before and are completely ambiguous, this is a pretty hard task. And just looking at the word itself, if you've never seen the word before, you're not going to do very well. So this is probably a good motivation to actually start thinking about how we can incorporate context-dependent features. And just give some corporate statistics. Of our def set, we purposely included more unseen ambiguous, just because it was more challenging that way. But if we just take a random selection, actually, these unseen words are, they're pretty rare, but it doesn't mean we shouldn't try and increase, these cases here, because they're much more interesting. So Klaus described one of the feature functions that we use, and it's the Longman preference one. And so what is this guy really doing? So if we look in the dictionary, we have the word kid, and it has these 5 entries. It's kid animal, like the goat, I think, and kid solid, kid, and then there's 3 other cases of for kid as a human kid. And basically, this feature function, what is it doing? Well, it's basically taking a set of these categories, A, S, H, H, H. So by using my example of angry kid, basically, we want to be able to describe adjectives by the categories and nouns that they prefer to modify in order to avoid sparseness. So to do that, so imagine that we can obtain a set of categories for both the head noun, kid, and the adjective, angry. So imagine that, so here's my set of categories for kid, and if I have, say, T and H, which is abstract and human for angry, then, we can do something with that. And maybe, maybe we can consider just simply concatenating them together, just merging them. So we have a big set of stuff here. Or we can do some kind of like component-wise multiplication, pruning, and we just end up with 3 human ones here. So why do we want to look at both of them? Well, simply merging them really introduces a lot of irrelevant categories. We throw in this extra one T, this extra one abstract, which isn't even in the dictionary in the first place. So, and this also increases entropy. But if we prune, then we remove the contextually irrelevant categories. We're saying, we see this adjective, and this adjective gives us some kind of clue about a particular category for this noun that it's modifying, then we can throw out at A and S. So how do we actually get these sets for of categories for the adjectives. Well, it turns out the Longman dictionary is actually pretty wonderful and actually has a bunch of adjective preferences itself. But upon closer look, some of them are actually pretty obscure. And maybe they cover like, all possible cases in the, language, but maybe we can get a more specific one. We can get one that's generated based on corpus. So in order to do that, what we can do is measure the entropy of each adjective. And by entropy, I mean, what I really mean is we just count up the frequency of each adjective and the category of the noun that it's modifying, and then and this is what I mean by entropy. Just sum of the probability and multiplied by the logs. And the idea is that we want to look for adjectives that have low entropy. Basically, that means that they're actually contextually useful. If it has high entropy, then it's probably not telling us very much anyway. And we also want to look at the frequency because it gives us a confidence of how reliable this adjective is. I mean, an adjective can have 0 entropy if it only shows up once, but if it only shows up once, it might not be very reliable. So my example here is angry. So my adjective is angry, and I look through my entire corpus, the training corpus, and I see that it has an entropy of 2.18, and and here's my vector of frequencies for each class, and it turns out it's 155 for abstract and 55 for human. And for this particular experiment, what I did was I basically just round this up, so I round this up to 2 and take the best 2 categories and assign it to my adjective angry. So I end up with the abstract and the human. And this is an experimental result. Like I mentioned earlier, there aren't that many unknown, unseen, and ambiguous cases. So this is also the motivation why we created this hard set, on top of the fact that we're a bunch of masochists and we like to do hard things. So here's some experimental results, and to compare with some of the previous context-independent features. So just want to skip most of them and come down to this one here. So if we just simply merge them together, we actually do worse. And it also increases the test perplexity. And I think a good motivation why this is happening is because a lot of adjectives can also be used in an abstract sense. And for lexicographers, if it can be used in any one abstract sense, it'll be in the dictionary for sure, and that turns out to be quite often. So sometimes we throw in, we're marking things that are abstract even when they don't even belong to that in the dictionary. But if we do this whole pruning thing, with the Longman dictionary of adjectives, we get a 1% of increase. And if we actually make our own set of adjectives, even the simple one, just looking at the entropy, then we actually get a tiny bit more increase from the previous one. Yeah. And that's about it for what I have to say. Is there any questions? Okay, I'm going to turn it over to Gia. Yeah. Oh, actually, wait, we have a break now, right?
Yeah.
Okay, so we have break time.
Oh, and the break time is pretty strict, so we'll come back at 7. We want to continue and stay on time.
Okay, our next speaker is David Guthrie. He's going to tell us about the adjective clustering, used a different way than with preference.
So many of the experiments our group performed demonstrated to us that it was very hard to pick features with such sparse data. And one thing we found that did help was creating clusters of our features. And we created 2 kinds of clusters, hard clusters and soft clusters. Hard clusters is we assign one word to one and only one cluster. And soft clusters, we let words be assigned to as many clusters as there was evidence for. This is how we did hard clustering for adjectives. We took a huge training data, which was almost the entire BNC, which is much larger than the training data we used for the semantic tagging. And it took all the unambiguous instances of the words in the dictionary and used these for training with the adjectives. And we created classes using the adjectives to modify these nouns, and we were able to compute the entropy of a class given an adjective. So using this entropy, we took the adjectives with the lowest entropy and made clusters for them depending on which semantic category they preferred the most. And we had heuristics for picking these classes with 2 thresholds depending on how low the entropy was and how frequent the adjective was in the training data and which category they predicted most. Then we used each cluster of adjectives as a contextual feature. We have some experiments. Our baseline was the most frequent tag as the prior, and we use the most frequent tag for a head word for scene words, and all words within the target noun phrase within the threshold of 10 occurrences. Adjective hard clusters were clusters that were defined by the most frequent semantic category, and also we did that using entropy for clustering. And noun soft clusters were clusters defined by all semantic categories. And we combined adjective hard clusters and noun soft clusters to get some results. So I don't know if you can read this. This is our baseline, which is 90.5, and this is adding adjectives, all adjectives. You see it went down because of the sparse data. Add only frequent adjectives, it's about the same as the baseline. And this is soft clustering for adjectives, improves it a little bit. So we let adjectives be assigned to multiple categories. Then entropy guided the selection of adjectives was selecting the classes based on the lowest entropy, and that did pretty well. And soft clustering of all head words improved a lot, but this was because the coverage was about 20% more than using this. And then the best result was soft clustering of the nouns and using the adjective clusters. And that's it. And I think Cassie is going to talk now. I also wanted to mention that all this is using GIA's maximum entropy toolkit, all these results. And yeah.
Cassia Martin is the third of our undergraduates. She's from Harvard, and she can begin to tell us about use of context in a different way.
As soon as it shows up. So I'm just going to introduce the use of parsing that we've made here and then talk a little bit about the structure and use of European WordNet. And then I'm going to pass it off to Fabio to present some results on those ideas. Okay, so the first thought, adjectives, nouns, clustering, very nice. Let's take a look at what we can get out of the syntax of the sentences we're using. We use the chaos parser built by Roberto Basili and Fabio Zanzotto, which is based on extended dependency graphs. So it's much like Catherine presented yesterday, except the difference, instead of a parse tree, we actually have lines between words, and the extended part means that we actually cluster by chunks, so we actually draw lines between like the noun phrase instead of the head of the noun phrase. The syntactic relationships we consider here is verb object, verb subject, verb prepositional phrase, and noun phrase prepositional phrase. So this table right here just goes to show when we throw everything into this toolkit the way it is with this information, we actually get results lower than the baseline. So this is to motivate that we need a little bit more intelligent methods for overfitting here if we use all the parsing information. And these results were also with GIA's maximum entropy toolkit. Okay, so this may seem like it's a complete side topic, but it's actually one of the methods we use to try to get these parsing results to be more useful to us. So I'm going to introduce the structure of European WordNet. The basic idea here is WordNet had at the bottom is a whole level of synsets for every noun. and which is just a directed graph at the bottom. But the level of base concepts, the top level generalizations in European WordNet is actually uniformly agreed across different languages, and it's got a tree structure right there. So we can actually take an example and say this sentence appeared in our training data that we have. Theo drove into the city. And say city might be tagged for us as a non-movable solid or something like that. Then the city would could belong to three different synonym sets. And the base concepts of that on the upper level of that pyramid might be things like urban center, administrative district, assemblage, so different ideas for what it means. But then above that, each of them has a direct line up to the top of the tree. So bottom level we call flat semantic fingerprint is just the very basic of the base concepts that noun, the city, actually means. And the entire thing is called the hierarchical fingerprint. Now, we did take all this information and introduced it as features, but if we just throw everything in as it is, we're actually getting 10 words instead of 1. So in and of itself, that doesn't help. But the idea here is to actually be able to figure out which of these ideas, which level of abstraction is most helpful to give us some sort of clusters of the nouns we're using. So if we can group city as a location with all the other things that are also locations, that'll give us information and actually reduce our scarcity problem instead of increase it. And the structure we use for verbs is a little different. Verbs in European WordNet don't have that same pyramidal hierarchy. Instead, it has like 1,000 top level concepts that it maps into instead of like 3 for nouns. But we take a lexicalized feature, which is just the one that's coming out of the parser. So we say the relationship here is verb prepositional phrase. So we take drove, we say our feature is drive underscore the phrase, the syntactic relationship underscore whatever preposition is actually used. There's actually a lot of information in prepositions. And then we take the actual lemma of drive, map it into Euro WordNet, and get the generalized features, which are drive, travel, and move. And then hopefully with our machine learning tools, we can figure out which of those will be the most helpful. All right, so now, unless there's any questions, I will give you to Fabio.
Okay, so now I'm here to try to explain how we use context here and how to get something informative from this context. Because that seems that somehow, if we take, for instance, the Pega word model of 50 words that represent the topic of the document, somehow we can figure out which is the category of the word. But what about the closed context, the one that is around the word? This is what we are trying to figure out here. We have seen some experiments about adjectives before, but now we want to see if something that seems to have, that means, for instance, the fact of being the subject of the verb to think, that this seems to be an important clue to select the information about the semantic category of the nouns related to this verb. How does in fact help? This is the problem. So if we have this positive observation, for instance, this wife thought he should eat more, or the waiters thought that Italians eat giant thieves. The first thing is because of my let's say shape. The second, because I have been in a restaurant and maybe I left too many small tips. So if we come out with these positive observations, we may, for instance, observe that given to the fact that our conceptual hierarchy contains female humans and male human, we can come up with this kind of probability of seeing the fact of learning that female humans are the subject of thinking. So this seems to be high and relative. This is what we can get. And if we come up with this idea, with this, let's say, example here, Fabio thought he has a good idea, he had a terrific idea before looking at the results. And what happens here is that eventually Fabio, that is not the word into the dictionary, may be classified as female. But I didn't think I am. So, what's wrong? That before, we have seen a talk before on how to group things afterwards. That means on how to take things, take the decision of the systems and to see into the hierarchy if they fit. The problem is not only that. We have to choose the right categories before actually applying our machine learning algorithm, because we want to see when the context can in fact prove and be predictive with respect to the concept we have. This is the real thing. So before doing that, and if you want to take profit of the context, we should collapse some categories. And this is the first observation. Then, we have, for instance, a document that has many instances of the same word. And these instances that does not have always the same, let's say, context, but they always mark human, generally. So, for instance, if we apply a posteriori our machine learning, the resulting model of our machine learning algorithm, maybe because of the fact we have, let's say, poor context there, we assign the category T, because T that means abstract, because of the fact we have poor context to suggest the right category. So why don't we stay with the famous idea of having one sense per domain, per document, sorry, and we try to translate it into having one semantic type per document. If it's so, maybe the information gathered from the other things, from the other instances of the same word, can make us the possibility of changing the category of the others examples. So before doing that, we should at least see if these conditions are correct in our corpus, and we have done that looking at all the instances in the corpus that are around 200,000. And if we look at the single WT per doc instances, we have used the set from 200,000 to 600,000, and the number we get is 1 over 200,000.
So that's just saying that you have 60K cases where, in total, where you have multiple occurrences of the same word.
Yeah.
Got it.
And this is the number of error we made with this assumption. So, now we have another problem, which is we have a lot of context and we have to select the information from this context. We can pull everything together and we can try to feed any machine learning algorithm with all this information, with this overwhelming information. This can be a solution. But in another case, some of these contexts are not informative so much. So this may be the problem. We would like to have, let's say, a representative of the word, of the behavior of the word into this context that says, for instance, which is the most important subject, in which is the most important verb, in which it has been seen as being the subject of this verb, the object, or which noun is the modifier, the modifier of, or other, to collect some other information that may be useful. And in order to do that, we decided to collect from the training, using the Moodle information, to collect from the training lists of possible verb subject, verb object, and modifier, and the other things here. They're ordering somehow in a list. And when we are looking at the context, global context of the word, we take the most important with respect to this list. And this list is ranked according to the Moodle information of the semantic category with respect to this feature that is one of this feature here. So what happens, in fact, is that the evidence comes across over on the fields, the slots, using all the evidence. So, to attack the problem of exploiting the context, as I said, the local context, that seems to be quite less informative than the other one, we used, let's say, a revised hierarchy that collects every female animal in animal, female and male animal in animal, female human and male human in human, female male and into animal. We use this one semantic class per discourse hypothesis, and this semantic fingerprint, that is the generalization of the noun into the basic concept of Euro-WordNet and the verbs on the topmost of WordNet.
Sorry.
And this is only the first talk about this issue, and in this case, the actual learning is based on a supervised method. So we will hear more about this issue and on how other things are used to do this. How these things are used to do this in a supervised manner, in unsupervised manner. So let's go to some results. We have this handout combined. That means the choices we have to do on this smaller set, on this set that is now combined, that takes 30,000 instances and 30,000 instances as test. Our baseline in this test is this 81.75. Putting the semantic fingerprint of the word, of the head word, the one we want to tag, so we are not actually looking at the context in this moment, we gain a lot. Putting some information about the context, we gain something more. So in any case, the context is helpful, but adding the hierarchical fingerprint, also this one boosts the result value. Now, just to, for these experiments, we have used our parser and the GR maximum entropy. So this is just to say that the effect here on the unambiguous words is interesting, and the effect here on the ambiguous word is interesting. It's just to say that we are not taking profit of the dictionary here, so this doesn't rise up to 100%, because for the unambiguous word on the closed word assumption, we should put the correct tag without looking at anything. But we are not doing that for the unambiguous word. So just to describe the results better and to compare with the one we have seen. And that's all for my talk.
I don't know. Good. I wanted to say something before I started. I joined this team because I'm interested in language modeling, and as Jordan actually remarked during the break, clustering is very important for language modeling. And we have this dilemma in language modeling, namely that if you do clusters the way we are used to, that is based on the statistical occurrence of words, then you know how to do clusters for words which don't need clustering because they have enough statistics. And what we really would like to do is to do clustering for words which don't have enough statistics. So I'm hoping that by an approach like this, which is so to speak linguistic, we'll be able to get around this dilemma. So, how do we do this? No. Which one do you? Okay, I've got to go back to this. I noticed you guys were pushing this.
You may just want to use the page
down. No, I'll just use the page up and page down. Okay, so what we're talking about right here is to introduce some unsupervised methods to labeling. And the problem is this, the motivation for this approach is this. We want to base maximum entropy features on lexical and grammatical relationships which are found in the context of the words we want to label. Now the problem is that, we can never have enough hand-labeled data to be able to use these features in a compound way. That means where we know that a word is surrounded by an adjective, and at the same time it's a subject of a verb. At the same time, I don't know, it has some kind of other relationships. These compound features we would simply never see enough. All right. So what was done so far in the project, maybe there is a probability of how frequently a word has a particular label. Maybe there is a probability at most how a word preceded by an adjective has a label, but anything compound just does not have enough statistical support to assign to it a target function for maximum entropy. So what I would like to do is to get more data, and as I said, it cannot be done by hand labeling. So the idea is to utilize large unlabeled British National Corpus for training and perhaps other sources, and also use the dictionary and perhaps initialize the process by the hand-labeled data, but otherwise carry it out from the unlabeled data. So first, some kind of a terminology. W is the noun to be labeled. Then R1 through Rm are the relationships in the context, like for instance, what's the immediately preceding adjective? What class does the adjective belong to? What is the what preposition is there whose object is the noun, and so far and so forth. That's what we mean R. C is the label denoting the semantic class that we want to label. And F1 through Fk is the label count, and in general, of course, for the label that belongs to the word, the count is 1, and for the label, and for all the other labels, the count is 0. So that's the situation, and these are the event files for the labeled part of the training data, hand-labeled part of the training data. But then we have to also be able to create these files for the unlabeled data, say from the British National Corpus, and there we're going to make the count fractional. And essentially what they will represent is the probability that that word has this label, that label, or some other label. And what we are going to do is we're going to initialize this fractional count by what we know are the probabilities obtained from the labeled part of the corpus. And the idea is simple. Louis already showed this around. Essentially, we so far have carried it out only on these two parts, and I will show some results on this part, namely that what we need to have is the annotated data and the unambiguous data from which we'll get those Q statistics that I had on the previous slide, and then we're going to do scale the probabilities over here after we do the training. In other words, there'll be some initial probabilities. With the initial probabilities, the fractional probabilities, we will estimate the lambdas in the maximum entropy way. After the lambdas have converged, we rescale what's over here and keep going. So this is the inner loop estimation. We get the counts. Inner loop is what was underneath there, and training for particular scaling of the BNC data. And as you know, counts determine two things. The counts determine which potential features will be selected as actual features. In other words, are these features reliable enough to be targets of the maximum entropy constraint. And secondly, once you decide that, how do you estimate the lambda parameters? And just to remind you how this goes, here are the probabilities, right? This is the probability distribution we're trying to estimate. This is some kind of a constraint function. In this particular example, is that the ice constraint function is determined by what category you want to label, you're paying attention to, what word you're paying attention to, and what relationship you're paying attention to, otherwise zero. So what we really have here is a marginal probability, and on the right-hand side we have the expectation of the constraint function relative to the empirical distribution. And of course, this is the probability form that we are aiming at. And now in the outer loop, I've already said, once the maximum entropy model is obtained, then we use the probability for each event file to rescale what the F values should be. And now we have an interesting phenomenon, which as far as I know is not in the literature, namely that because there is this rescaling constraints or features that were reliable previously may no longer be reliable now because things have been rescaled and possibly new features become reliable because, again, of the rescaling. So we have this kind of a moving target, and well, and that's a problem. Here is some results which were run by Jia Kui, and you can see that that in fact we don't have total success. The performance is improving for a while and then it gets worse. And of course the question is why. Then is why is that the case? Is it that simply we are overtrained, or is it that this moving target of constraints is something that is not going to allow us to converge? What are the problems? Here are some lists. You know, if you cut it off at the point at the lowest point, then you can say that the results are promising. But of course, the method requires theoretical and practical exploration. This changing of feature and feature targets is a new phenomenon, as I pointed out, and I don't know what it does. And there is, of course, also a question of a careful selection of relationships, so there are not too many relationships on which you target, and so that they don't force you to overtraining. And later on, you will see a proposal by Jia Kui and David Guthrie to explore this phenomenon.
Any questions?
Yeah, thank you.
So it's always difficult to have a talk after Fred because of his clarity, and now I have not the excuse of being not a native speaker because he is also not a native speaker. So I will go and talk about a line of this project that is the attempt to explore the use of external resources other than the training material for semantic tagging. And after some motivation, I will discuss experiments and results of three tasks. First of all, the need of going from the lexical knowledge base that we used, that were WordNet, to the long-man semantic labels that we were finding in the training material. And we had developed a tagger that was bootstrapping using WordNet. And the use of this tagger as a way of estimating the empirical distribution Fred was discussing before. So all experiments are showing us that the lexical information is critical. So if you know about the lexical item, you can do a very good job. but and the context is quite limited in giving us information. So as the word census ambiguation literature is showing, we need to combine different resources. And I'm also very interested to application of this technique. That means the possibility of starting with the information porting, the information extraction system, for example, throughout domains. So it is possible that you do not have the time to develop an annotated resource. So you should minimize the cost of annotated resources. What is the contribution of WordNet? WordNet is a source of evidence for the lexicals that are not in the source dictionary, for example. There are some words that are in Longman and are not in WordNet and vice versa. WordNet is also giving, thanks to its hierarchical organization, a consistent way to generalize that Fabio was just suggesting. And WordNet can be used to constrain the way of estimating the word uses in the corpus. What we need is also to estimate the similarity between words. And I would like to suggest that if we can look at syntactic similarities in the corpus, that means word uses that are similar each other, we can try to use this as a cue for semantic similarity, and this is a cue for the empirical estimation. In fact, what we would like in the WordNet hierarchy is to find specific hypernames of some words that are generalizing enough to separate the senses of the words, but that are also enough general to keep the number of word classes limited. If we keep the number of word classes limited, we can have less features in any statistical model. Why syntax is interesting? Of course, if we look at words in a specific grammatical position with respect to one verb, for some of them we have enough evidence that they are a kind of liquid, for example. But for other of them that are usually appearing with some other semantic kind of nature, we can constrain this word in this specific position to be also liquids. And this is true for several kind of syntactic positions. Here we are seeing the subject of the verb succeed, and possibly knowing that president, director, kids are humans is teaching us that these words in this kind of position should be constrained. In some way, we are trying to pass from, let's say, trigram probability to class-based probabilities, right? And we have two kind of effects. First of all, we can decide what is, let's say, a good class when we see a verb and a specific relation. So we are constraining through the context. And this is a selection of preference that we can collect from the corpus. And at the very end, because we know which are the nouns that are in this kind of context, we also can gather information with respect to the lexical model. And this lexical model is usually written in the dictionary in a quite generic way, but in the corpus can be quite different, because we know that the word usages in the different domains change dramatically. So I would say that the first is a lexical evidence and the second is contextual evidence. And the plan is to take the contextual evidence when it's enough reliable to gather this information and then reflect this in the lexical evidence. So we want a lexical model that is reflected from the context. And we are trying to estimate the first, and the second is a side effect. How can we estimate? We, in these 6 weeks, tried with a similarity measure that is called conceptual density, that is attractive for its efficiency. It can be, let's say, derived easily. Some basic terminology for determining the similarity metrics. We have a target noun set, for example, the subject of a given verb. And we can look in an hierarchy to the branching factor, that is the average number of children of any node under an hierarchy that is rooted to a given scene set. And then we say that this hierarchy is, let's say, dominating some of the nouns that are called marks. So a noun is a mark if it is represented by a synset, by one of these sense under the hierarchy rooted in S. And I will refer to the number of this noun with n. So each the synset is dominating enough noun, and these nouns are exactly n, capital N. And then we call area of the sub-hierarchy the number of its nodes. The conceptual density is a trade-off between the generalization and specificity of the way we traverse the hierarchy. Imagine that our target nouns are 3 words and they have different senses. They are entering in the hierarchy in different levels. The idea is that the node that is 1 is represented correctly all the 3 words. So we could stay with 1, but possibly 1 is not usable because it's not disambiguating any of these nouns. Is completely, let's say, it is not able to decide what is the notion of the word 2, for example, or 3. So 8 is good because it's not disambiguating the word 1, but it's disambiguating the word 2 between the sense number 8 and 11 in that picture. And maybe it's a good interpretation of these 3 nouns, these 2 distinctions that are 8 and noun, instead of going up to 1. Well, one could say that 2 is also representative instead with a minimum description length principle in mind, we can rise up to 2 and have just 1 node instead of 2 for representing. But usually the higher you go in the hierarchy, the more material you are entering in the hierarchy because the number of children of 2 is possibly growing and you are including a lot of irrelevant material. How can we capture this with the previous definition? We can decide that the conceptual density of the synset S, for example 8 or 9, given a syntactic relation R, is given by the ratio between, okay, in the denominator you have the area that is computed from WordNet, is the real area of that tree, and in the numerator you have an estimation of a tree that is representing n object, giving a branching factor of nu. The distinction between these 2 cases is due to the fact that some branches in an hierarchy can have a branching factor of 1. So they be generating a list and that formula is giving us bad results. So an idea using this conceptual density, imagine that we have these 5 subjects, potential subject of the verb to march. We want to find a smaller set of synsets that are representing all the nouns and that maximizes the overall conceptual density. So the system is coming up with these 4 synsets. So we have 5 words and 4 synsets, and the words are dominated in the following way. But we see that the synsets are not independent because they are dominating each other sometimes. For example, an organization is a generalization of the army unit notion. Or we can say that a mammal is an animal or animate being. And the way the words are distributing here is that troop and division are of course army unit, but if you want to cover also the sense of horse, you go up and you pick up with the sense 1 the 3 words. So it's a nice partition of the nouns. And most of the nouns, although they are quite, for example, division, they are quite ambiguous, are totally disambiguated here. And horse is not disambiguated, although it is reducing the number of senses, because 2 of its senses are kept. Let's see how we applied this technique. For example, we have to map from WordNet synset to Longman classes. So every lexical entry in a Longman dictionary has a definition in terms of a semantic tag and a subject code. And in particular, here you see that liquid and food are related to one definition of stuff. So the similarity metric has been applied to all the nouns that have the same class and the same subject codes. So we used as the target noun set a subset of the dictionary, and we tried to find out the interpretation. So the outcome of the system is an explanation of each of the lexical entry that has a given semantic class and subject code, given the constraint that the other words are in the same cluster. And for each WordNet, for each synset in the WordNet hierarchy, I have a mapping in the Longman class that are pointing to it. So we can compute the probability that the WordNet synset is appropriate for a noun given the Longman dictionary class for it. And then when we have all of them available from the noun in Longman, we can compute the probability of the Longman class given the noun and a given WordNet. So by traversing the hierarchy of WordNet, we can go to Longman, and this table here are giving the vice versa. So, for example, if we take a cluster like abstract and solid, the strange class that Luis was mentioning is related to this kind of 5 words. It's nursery school, polytechnic school, seminary, and senate. And we see that the synset that is pointed is school has a coverage of 60%. If you want to go a bit upstairs, you go to educational institution and you reach 80% of coverage. And if you want to include also senate, that is not considered as a school in the WordNet hierarchy, you have to go up and you include also senate, but you are losing some other words. To give you a complex example, let's look at the stock word that has a number of senses in WordNet and in Longman. We see here, for example, capital letters like T, J, N. You have been listening to them. Again, T is abstraction, J is a movable solid, N is no movable solid, and A is animal, right? And these are the definitions. If we look into the definition for A, and we look into the probability that have been assigned to the WordNet mapping, we see that stock has a breed, strain, stock variety sense has received a probability very high, and the remaining probability are capturing the other sense that is again mammal and animal breed. If you go up in this hierarchy, you go to object, physical object, but you are losing this kind of preference for the system. And if you look to the stock as a non-movable solid, you see that it's an artifact, object, physical object. No movable solid in Longman is not, let's say, well represented in WordNet because movability is not an issue. It's a sort of orthogonal issue that has not been used in any WordNet distinction. So you have objects and artifacts, and it's appropriate for the sense number 2 and 3 there. And if you're looking to plants, again, you have a sort of much smoothed probability distribution, but you are capturing the right synsets. And if we look to the category mapping, for example, we see that human are pointing most of the times, as the probability is suggesting, to correctly to person and organism, while inanimate is less, more, let's say, more confused and fuzzy category because it's giving you substance, matter, artifact, cognition, knowledge. And this has been totally, let's say, automatically derived. I have no figure of performance because I don't know how to, let's say, measure this quality. But we were using this mapping for deriving probability from WordNet and tagging the corpus. So the idea is that if we can derive the probability for WordNet and map this probability to labels in Longman, we can try to apply this in a very stupid Bayesian framework in which the combination of features is taken as the product of the different features, preferences, and then we maximize through the classes. This gives us the possibility of tagging each context. And these are the results for the kind of hard set, the handout data and the blind data. And
can I ask a question about WordNet? In this particular example, there's no attempt to use extract. Is there some attempt to extract information in WordNet that deals with the context as well, or is this just the probabilities of the individual words mapping into categories you're playing with now?
No, this yes. In order to derive these quantities, I am looking to all the nouns that are in a position that are fits in a relation R. That means they are all the subject of the same verb or all the object of the same verb. And this is corpus statistics, right? And so this is totally dependent on the corpus. What I was not using are the information about the labels that I was finding in the training material. This has not been used because I was willing to, let's say, explore a totally unsupervised track. But of course, I would like to compare these probabilities with those that are coming from the training material. And in a sort of co-training way, you could try to estimate this probability in an unsupervised way, compare with the training material to see if they are let's say, coherent with the true and controlled material. And if you decide that this is not true, you can just retry later when the less ambiguity in the corpus is there. So you can go in an incremental way. This is one of the things that we were thinking. But this is working also for other domains. So this gives also the possibility of cross-domain comparison of these results. So we have the results for the hard set that are around the baselines that other tests have been found. So this means that in a totally unsupervised way, without looking at the tag, we are doing more or less the same than the supervised method. And if we look to the edge distance that was presented by Chris, that is trying to take into account the similarity between the hierarchical classes according to the hierarchical organization, these are the results that are in some sense more acceptable. And so, for example, for the blind corpus, that is the easier one, we have better results. So this means that the probability that we are deriving is consistent with the target material. That means that we are moving towards a space in which we are assigning this distribution in a very consistent way with the work done by the annotator, and this is a good news. Consider that these two last results for the held out and blind have been obtained by exploring more or less taking from the training corpus a number of words and analyzing the probability that we were talking about for only 2,000 of those words because of the data sparse test problem. So only for 2,000 words we had very good probability estimated from the kind of relations. The other relations were not giving us good information. So we have not a good coverage of the training corpus. We expect to, when we can process the entire DNC, the 28 millions, that this number is increasing, at least 50% of the corpus is giving us enough information. And then, if we look at the overlap between the words that are in the training, the words for which we have been training the system, and the entire set of words that were in the held out and blind, we have less coverage of half percent. So very often the system is giving information that is not reliable enough. Then again, another outcome of this work is to try to re-estimate the probabilities for the maximum entropy model as a way to derive the empirical distribution and the bootstrapping approach that Fred was suggesting. And I'm sorry, but we couldn't conclude these experiments. So in these cases, this is a result in which we were just looking at the training data, labeled training data with all the syntactic features of all with the Edwards. We were feeding the maximum entropy toolkit. And then we were repeating this experiment, looking at the training data plus the empirical estimation using on the held out using WordNet. So we trained the data. We took the training data with the labeled example. We had the empirical estimate for the held out using WordNet. We are combining the two, and we were feeding the maximum entropy toolkit, and we were increasing every time the performance. But these experiments are not conclusive and need some more exploration for representing the features. So we were just using a robust parser, not the best one possibly, so we have to repeat this experiment with other parser to assess the information of the syntax. and our results were consistent with the fully supervised method. Open issues are have more corpus material. Try with alternative formulation of similarity metrics and assess the Longman dictionary to WordNet mapping to reflect this in the currently annotated BNC portion. And I was concluding this part. If there are some questions on this, maybe it's better to have them now.
Put on the schedule.
Now I should go for the, let's say, survey of what we were hearing, and I would like to then to give a break to the audience, and the remaining time will be spent on the student proposal. Is it okay?
Yeah, I think it would be good to have a break now.
Maybe a break now and then the conclusions.
Okay, so it is 11:20.